Math 1332, Chapter 2, Set Theory, Section 3, Using Venn Diagrams to Study Set Operations, Video 6, Finding the Cardinality of the Union of Two Sets. This will be the last video in this section, and it'll bring to the surface a pretty, maybe not intuitive formula, but once you see it in action, it might actually be fairly intuitive. And it involves, as the title states, finding the cardinality of the union of two sets. In order to get you to see this, or dare I say discover this formula, we're going to set up a scenario, and I'll just ask you a few questions. Suppose set A contains, let's highlight these while I'm reading it. All right. Suppose set A equals the set containing the letters A, B, C, D, and E, and set B equals the set containing the letters D, E, F, G, and H. Find the following. Cardinality of A. Remember that the lowercase n means cardinality of a set, or equivalently how many elements the set contains. Cardinality of B. And the cardinality of A union B. Now, of course, since we don't have A union B yet, we'll have to find that, and then we'll find its cardinality. On the surface, these problems seem pretty straightforward. So let's go ahead and see how they look. For the cardinality of A, we simply, well, first off, I got to write that a little bit better. There we go. For the cardinality of A, we simply have to count how many elements A has. 1, 2, 3, 4, 5. Well, that was easy. Hooray for easy. For question 2, same thing, cardinality of B. 1, 2, 3, 4, 5. Okay, so they both have 5. For the third part, we're going to have to find the union. And recall that the union of two sets is the set that we get when we join them together into a single set. If you use the ramen noodle flavor packet analogy, that means that we take this flavor packet, open up both of them, dump them together, and see what all that we get. Well, set A contains 5 elements and set B contains 5 elements. So if we combine two sets, each containing 5 elements, how many elements would you expect it to have? It's kind of a rhetorical question, but also kind of not. All right. In order to find the cardinality, we first have to find A union B. Well, A contains A, B, C, D, and E. So we'll start there. And now when we open up set B and join its elements, B contains D and E, but notice D and E already written there, so we don't have to write them again. And they bring in F, G, and H. And now that we have the set A union B, we can calculate its cardinality. Or rather, I should say count its cardinality. 1, 2, 3, 4, 5, 6, 7, 8. A minute ago when I asked you, when we take the union of these two sets, A has 5 elements, B has 5 elements, how many elements will their union contain? Did you say 10? Because 5 plus 5 is 10? You might have, you might not have. But on the surface, you would think that when you combine two sets, the cardinality would just be the sum of their two cardinalities, because we're taking the elements of the first set and the elements of the second set and dumping them all together. But in this case, that didn't happen. So let's just make a note here. Rather, let's just observe. I'm not sure where I can write this, but I guess I'll write it there, and I wanted it in blue. Let's observe in this case that the cardinality of A plus the cardinality of B did not equal the cardinality of their union, even though their union is obtained just by combining their elements. So my question is twofold. Number one, why not? How come when we combine 5 elements plus 5 elements, we didn't get 10 elements? And number two, is there a relationship between the cardinality of the union of two sets and the cardinalities of the individual sets themselves? Some of you might be able to see through this, but if you haven't seen through it yet, I think what might help us is a real quick Venn diagram of these two sets. Now, granted, we did not declare any universal set. I guess a reasonable universal set would be the set of all letters in the alphabet or something like that. But we'll just go ahead and set up a Venn diagram real quick. And instead of taking the time to type everything in, I'll just draw everything in. Here's our universe, which wasn't declared. Here's set A and set B. Recall that set A contained the letters A, B, C, D, and E. And that set B contained the letters D, E, F, G, and H. Also recall that in a two-circle Venn diagram and a two-set Venn diagram, our regions are numbered 1, 2, 3, and 4 accordingly. Let's make that 3 a little bit better in the middle. And so now let's put all the elements in each set into the Venn diagram in their proper places. Starting with the letter A, which region would A go into? Well, it belongs to set A, but not set B, so A would go in region 1. And who else would go in region 1? B and C, because both of those belong to set A, but not set B. But what about region 2? Who would go in region 2? Well, D would go in region 2 because it's in both sets A and B, but so would E. So D and E would go in region 2. And then let's use orange. And then the rest of the elements in set B, the elements F, G, and H, would belong to region 3 because those elements belong to set B, but they do not belong to set A. And again, normally we would talk about what lives in region 4, what's in the universe. It's in none of our sets, but in this case, we're not worried about that. So there are 5 elements in circle A, 5 elements in circle B, but altogether there's only 8 elements. Why? Because some of those elements were counted twice, namely the elements in the intersection. I think this is worth typing. Notice both cardinality of A and cardinality of B account for the elements in the intersection of A and B. Thus, when we add cardinality of A plus cardinality of B, some elements get counted twice. Not just some elements. Specifically, the elements in the intersection, A intersect B. I don't like using a lowercase, excuse me, I don't like using a lowercase n for intersection, but when typing it, it works in a crunch. Specifically, the elements in the intersection, A intersect B, get counted twice. Thus, when counting the elements in the union, A union B, adding the cardinality of A plus cardinality of B double counts the elements in the intersection. Hence, the cardinality of A plus cardinality of B is over by that amount when calculating the cardinality of A union B. Well, that was a lot more words than I intended to type, but let's do this in pictures because pictures are cool. When we added up everything, oh, it's not supposed to be that, hold on. There we go. When we add up the elements in this circle with the elements in this circle, the guys in the middle got counted twice. And so saying 5 plus 5 gives us a total number of elements is over by 2 because the 2 elements in the middle got counted twice. So we have to knock it down by 2 to bring it to the correct count. So what does all that mean? In other words, it means this. If we want to calculate the cardinality of the union of two sets, we can start by adding the cardinality of the first set plus the cardinality of the second set. But the guys in the intersection in the middle, in this case, it was these two elements in D and E, they get counted twice, once when we write the cardinality of A and once when we write the cardinality of B. And so since we counted them twice, we have to remove them once by subtracting the cardinality of A intersection B. And this is your formula for the cardinality of the union of two sets. It's the cardinality of the first set plus the cardinality of the second set minus the cardinality of the intersection. So how would this look in a word problem? Well, let me pause the video and I'll type a problem and then we'll see how this works. All right, let's take a look at this example. In a class of 20 students, 12 students are biology majors, 9 are chemistry majors, and 6 are both biology and chemistry majors. That word was kind of important, and in retrospect, I don't think I need these parentheses. Originally, that number wasn't going to be needed to calculate anything, but since I put this follow-up question, it will be. You'll see what I mean in just a moment. All right, so let's read the question again, this time with some highlighting. In a class of 20 students, 12 are biology majors, 9 are chemistry majors, and 6 are majors in both biology. Bad grammar. 1 second, folks. Maybe I should have reread it when I had paused it. All right, plus I'm going to get rid of this highlighting. We really don't need it. Just being a little silly there. Not silly. For some people, it helps. But right now, I'm too busy fixing the grammatical issues. All right, in a class of 20 students, 12 are biology majors, 9 are chemistry majors, and 6 are both biology and chemistry majors. Now, first off, this might seem like an impossible situation because we're saying that the class only has 20 students. Here's 12 of them that are biology majors and 9 of them that are chemistry majors and 6 that are both. Now, how could that be? Well, imagine you're in a classroom, you're a teacher of a classroom, you teach some science class, and there are 20 students in the class, and you say, all right, raise your hand if you take biology. Excuse me, raise your hand if you're a biology major. 12 students raise their hand. All right, hands down. All right, now raise your hand if you're a chemistry major. 9 students raise their hand. 12 plus 9 is 21. How could that possibly be? Because some students raise their hands each time. They got counted twice. Now, raise your hand if you major in both biology and chemistry. 6 students raise their hand. So those 6 students got counted in all 3 of the counts. They raise their hand when I said who's a biology major. They raise their hand when I say who's a chemistry major. And they raise their hand when I say who majors in both biology and chemistry. All right, so this is the questions we're going to answer. How many students in this class major in biology or chemistry? Emphasis on the word or. And how many major in neither? Now, speaking of emphasis, you might have noticed that the word or and the word and were both in caps. That was for emphasis because we're talking set theory, sets, unions, and intersections. And when you're talking verbal interpretations of union and intersections, we've mentioned this in a previous video, but the word and is associated with the intersection of 2 sets, and the word or is associated with the union of 2 sets. The fact that they're giving us numbers, how many are in each set, tells us that they are giving us cardinalities. So to answer this, let's kind of organize our information for a moment. Let's let capital B be the set of biology majors in the class, and capital C for chemistry be the set of chemistry majors in the class. See if we can get all that on one line. All right, now let's write down what we're given. We're told that there are 20 students in the class, but not quite sure how to represent that in terms of biology majors and chemistry majors. But we are told there are 12 biology majors. So we're told that the cardinality of set B is 12. What about the 9? What does that represent? Well, it's the number of chemistry majors, so it's the cardinality of set C. But what about the 6? When I say biology and chemistry major, that's the intersection. Remember, you belong to the intersection if you belong in the first circle and you belong in the second circle. So when they say there are 6 students who are both biology and chemistry majors, they're telling you that the cardinality of the intersection is 6. And what are they asking us to find? Find how many students in this class major in biology or chemistry, or means union. And since they're asking how many, that's the cardinality of the union. So we went with the cardinality of B union C. And I just realized I used A and B instead of B and C up here. It's what happens when you always use the same generic sets. All right, it'd be nice if we had a formula for this. Oh, wait, we do. Recall that the cardinality of the union is equal to the cardinality of the first set plus the cardinality of the second set. But that would be impossible in this case because 12 plus 9 is 21 and there's only 20 students in the classroom. The reason it's over and the reason it's wrong is because when you add the cardinality of the biology majors and the cardinality of the chemistry majors, anybody who belongs to both is getting double counted, and hence we have to subtract the cardinality of the intersection. We have all these values. We know that there are 12 biology majors. We know that there are 9 chemistry majors. And we know that 6 double major. So what's 12 plus 9 minus 6? Well, 12 plus 9 is 21, but 21 minus 6 is 15. Therefore, 15 students in the class major in biology or chemistry. I do want to remind you that the or in this context is the inclusive or. So when it says biology or chemistry, it really means biology or chemistry or possibly both. So at this point, we've answered the first question, how many students in this class major in biology or chemistry? But the follow-up question, how many major in neither? Well, picture the class again. You got 20 people in there. Raise your hand if you're a biology major. 12 people raise their hand. Raise your hand if you're a chemistry major. 9 people raise their hand. Some people to raise their hand when they said biology. All right, raise your hand if you major in both biology and chemistry. 6 people raise their hand. And the professor is losing count, so he's like, all right. Raise your hand if you major in biology or chemistry or both. How many people raise their hand? 15. How many people don't raise their hand? The rest. Also, the 20 minus the 15 is equals the 5 students major in neither. Because we know that there were 15 that major in one or the other or both. I want to wrap up this video by just going back to this formula for a brief moment. This formula can actually be used in a variety of ways. As with any formula, it should contain more than one unknown, because if it doesn't, if there's only one unknown, then it's really just an equation that you solve for a value. But anytime you have a formula that relates unknown quantities, it's really a formula for any of them. The example we just did, you were given these, and you were asked to find this. But that's just because of the 3 pieces of information I was given. If I were given, say, the cardinality of each individual set and the cardinality of their union, which I could spot because it uses the word or, then I could find the cardinality of the intersection, which would be asked using the word and. But in general, any formula that has a bunch of unknowns, as long as you know all of them, you can almost always solve for the last one. And at this level, it's an always. There are some formulas that are impossible to solve for one of the unknowns, but if it just involves addition and subtraction like this one does, it doesn't. There is one more thing I did want to mention, that there is a version of this formula for 3 sets. I'm not going to hold you accountable for it, so if you're tired of watching the video, you can stop now. But I just want to show you what it looks like to warn you that as you increase the number of sets, the formula gets uglier. Those are all unions. If you had the union of 3 sets, it would still start out with the sum of the cardinalities of the individual sets. But just like in the original formula, some things are getting counted more than once. For example, if you belong to both A and B, you got counted here twice. So I have to subtract the cardinality of that intersection, because if you belong to A and B, you belong to its intersection. But that's not the only people that got counted twice. If you belong to A and C, you got counted twice, once here and once here. So I would have to subtract the cardinality of A intersects C. Or if you belong to B and C, then you got counted twice, once here and once here. So I would have to subtract the cardinality of B intersects C. So more sets means more intersection pairs you have to account for. But it gets even worse than that. There's one piece missing, and it's not obvious why. Let's say you belong to all 3 sets. Let's say set A is your male, set B is your professor, and set C is you have a daughter. So I belong to all 3 sets. Then when counting the people in the union, I would be counted here and here and here. But then I would be removed here and here and here. So I got counted 3 times, and then I got taken out 3 times, and now I'm not getting counted at all. Why? Because I belonged to the intersection of everybody. So to bring me back in, I have to add the cardinality of the triple intersection, A, B, and C. Like I said, you're not going to have to use this formula, but I just wanted to point out that even if you just add one more set, the formula gets a lot more convoluted. If you were to look at another layer, another level up where it was the union of 4 sets, you would start noticing patterns and be able to see, okay, I see what's going on, and I see why it's getting messier every time. What you need to know is this formula, and this is a pretty reasonable example that demonstrates it.